Okay, I am going to talk about the trial practical test using SPSS to show you how to approach the answering the questions. So note that it starts off by saying once the test is released you have 3 hours to complete the test and you must submit your answers within 3 hours, otherwise you will be subject to penalties. So the first question is worth 4 marks and this is based on your first workbook. It's basically a data cleaning exercise. We're using the SPSS file trial.south, which you can download with the trial practical test. We have 5 variables: subject ID, hours of sport, which is a metric variable because it's hours of sport per week, sex or gender, which is obviously categorical, dichotomous, female and male, hours of work, which is hours of paid employment per week, also a metric, and then fitness level measured on a scale taking values from 0 to 10. Again, this is metric. Now, when you're doing your data cleaning, you need to take note of the scales used. So hours of sport and hours of work can take on any positive values, but any negative values are out of range. Sex can take on the value 0 to 1, and anything outside of that is out of range. Fitness takes on the values 0 to 10, and anything outside of that is out of range. The exception to all of this is if a missing value has been assigned, a missing value code has been assigned. So for the hours of sport and hours of work, the missing value code is likely to be -1. So you need to check in your SPSS file that this missing value code has been assigned. If it has, then values of -1 are valid. If not, then you need to assign the value code in SPSS, which I'll show you now. So it says perform some elementary data screening on the 4 variables, hours of sport, sex, hours of work and fitness. Remove any cases involving outliers from the file and replace out-of-range values with a user-defined missing value code. Record the value of subject ID and the value for all out-of-range values and outliers in the table below, just like we did for workbook 1. So we always start with out-of-range values first. So let's go to our trial.sab file. First thing I always do is just check to see which variables have been assigned a missing value code. So you can see hours of sport has been assigned a missing value code of -1, hours of work has, and fitness has, but sex hasn't. So sex takes on values of 0 and 1, so we might assign you a missing value code of 9 or -1, it's up to you. And before we do that, let's run some preliminary descriptive analyses on these on each variable to see what values we have. So for the categorical variable, we'll go descriptive statistics and frequencies, put sex into variables, select OK, and it will tell us exactly which values we have. Go to our output file. You can see here that 610 cases have been assigned a value of 0 for women, 647 have been assigned a value of 1 for men, and 1 has been assigned a value of 9. Now we've already noted that sex has not been assigned a missing value code yet, so this value is currently out of range. In order to establish which value it is, we'll go to sex and we'll go sort descending, so we get our value of 9 at the top, and you can see it's still got a subject ID of 1127. So we go to our answer document and we write 1127 in the subject ID box and the value of 9. Okay. Also make sure that you go into SPSS and you assign a missing value code of 9 so that variable will no longer be out of range. Okay. So now we'll do the metric variables. So for the metric variables we'll go descriptive statistics, descriptives, pop them in to the variables box. That should be okay, we've got the minimum and maximum there. So hours spent playing sport can take on any positive value, so we've got a value from 0 to 8, so that's okay. Hours of paid work per week can also take on any positive value, which is 0 to 75, which is okay. Fitness level can only take the values from 1 to 10, so this is there's a value of 14 there, which is not okay. So in order to identify which subject ID has the out of range value, we'll go into the data view and sort descending, and you can see subject ID of 1588 has a fitness value of 14, so you need to make sure you write this in here, Under fitness, 1588 has a value of 14. Okay, so that's our out of range values. Now make sure we assign a -1 value for that, so that's no longer out of range, it's now missing, it's taken on the missing value code, so it won't be included in analyses. So now we need to check for outliers, so you can go analyze. We only have outliers on metric variables, not on categorical, so we'll just do this for the metric variables. So we'll analyze descriptive statistics, explore, and we'll chuck our metric variables in here. We are happy with those statistics, we can ask for the plots, and we'll take away the stem and leaf because it's useless. Select histogram, press continue. Don't need any other option. Oh, yes, we do. Exclude cases pairwise. If you don't exclude cases pairwise, then any variable with a missing value will be excluded on any one. Any cases with missing values on any one variable will be excluded from all of the variables if you don't press exclude cases pairwise. So make sure you select exclude cases pairwise, so all of the valid cases on each variable are being examined, regardless of which other cases have invalid values on other variables. Okay, so make sure you select exclude cases pairwise. And there's our descriptive data, but we'll go down to the plots. Make sure you look at both the histogram and the box plot. So you can see hours spent playing sport each week doesn't seem to have any outliers. There's a bundle of values at the top, but that just looks like positive skew because they're not really clearly distinct from the box plot. They're quite close to the tail, and you can see in the histogram there's a bit of positive skew there. And then hours of paid work per week, you can see there's a value up near 80 that looks like it's out of range, and this also shows up on the box plot. Now the box plot will give you the current, this is driving me crazy, the box plot will give you the current row number for these out of range values, but we need to go in and actually identify which values these are. So this is on hours of paid work per week. We'll go into hours of paid work per week, and we'll sort descending because it was a strongly positive value. And you can see that both subject ID 143 and subject ID 821 each have extremely positive values of 75. So you need to note these values down in here. So put hours of work, the two subject IDs and their values of 75 in there, and then you need to actually delete these outliers. Okay. And then finally fitness looked fine because it can only take values from 0 to 10, so it looks good, there's no outliers there. So the final thing we need to do is produce the new frequencies and descriptives table for each variable. So we press OK for sex, and if we compare that to our solutions, we've got 48.4 and 51.6. Oh, actually, we'll open the solutions. It's right here, so you can see here the box looks the same, the frequency box looks the same, which is what we want. And we've got to analyze descriptives, explore, and we will select. We actually need to look at, you can produce all three in the test, but we only need to look at these two because we only need to look at hours of paid work per week because it was only for that value that we removed the outlier. So we don't want to do explore for that, we want to do descriptives. Just press OK on that. So we get the new descriptives for each of the variables, and so if you compare that to the solutions, you'll see that it's the same. Okay, so that's the end of question 1. For question 2 now, we're using the trialprac.sav box. Data file, sorry. We don't want the solutions, we just want the question document. So question 2 and 3 both relate to the data in the file trialprac.sav. This is a sample of data collected from a survey of Australian adults. The variables included are age, education level, sex, dominance, assertiveness, self-reliance, compassion, warmth, sensitivity and sense of self-worth. More information about each variable is given in the labels in the data file. You should assume that if a variable has no value labels, it is measured on a metric scale, and you should also assume that the data was collected using a random sample. Perform a two-stage hierarchical regression with sense of self-worth as the dependent variable and including 5 suitable independent variables from the list above. Include in the output all statistics and graphs you think appropriate. There is no need to do any data screening on this data and do not recode any values. So what did we look at to establish that the predictors you chose were suitable? The first step is to make sure you can only, as you guys would know by now, you can only include metric variables or categorical variables that are dichotomous. They're the only types of variables you can include in a linear regression. So the first step is to go to our trial prac.sav file, go to the variable view, and have a look to see which one's a metric. So the question page said that any variable that doesn't have labels on the values, we can assume a metric. So we know age is metric, compassion is metric, sense of self-worth, which is the DV, is metric, assertiveness is metric, dominance is metric, and self-reliance is metric. Of the remaining 3 categorical variables, we can only use those that are dichotomous. They only have 2 categories. Male and female does, so we can use that. Education has primary, secondary and tertiary, so it's not dichotomous. It's got 3 categories, so we can't use that. And then sensitivity also has 3 categories, not at all, a bit and very sensitive, so we can't use that. So straight away we will exclude education level and sensitivity. Oops, not dominance. So you need to go into your answer sheet and say dominance and, not dominance, what was it? Education level. Sorry, this is my touch screen. Education level and sensitivity were not included, and we can say because they are categorical variables with more than 2 categories. Now, that leaves us with 6 possible dependent variables. We are only supposed to use 5 dependent variables. We might exclude a variable for conceptual reasons, but first of all let's run a regression, do some preliminary analyses and see how the remaining 6 possible predictors work together in a regression. So we'll go up to the regression, we'll say analyze, this isn't our actual regression, this is preliminary analyses. Go down to regression, linear, put our DV, sense of self-worth, in the dependent variable. We can put sex in as a predictor, age, sex is a categorical variable with only 2 categories, age is metric, education level we can't put in, compassion and warmth we can, assertiveness we can, sensitivity we can't because it's got 3 categories, dominance we can, and self-reliance we can. We go into the statistics box. I always select all of these, but for this particular preliminary analysis you don't really. What we're interested in is the collinearity diagnostics here. That's what we're actually interested in. We want to see, check for any multicollinearity. If there is multicollinearity between these variables, we need to exclude 1 or 2 or however many until we don't have issues with multicollinearity. So press OK, continue, and OK. We go to our output, and we scroll down, we have a look at the tolerance values. So you can also see in the correlation matrix here at the beginning, there's no correlations greater than 0.8 between any of the variables, so the intercorrelations between the variables are okay. But you can still have multicollinearity in the sense that some variables can add together to predict the DV. Or there's other ways in which multicollinearity can be an issue, not just with straight raw bivariate correlations. And there is actually a correlation here between assertiveness and dominance. It's getting close to 0.8, so that could also be a problem. There's some quite high correlations here between dominance and self-reliance as well. So let's go down and see if they are actually a problem by having a look at our tolerance statistics. Now, any variable with tolerance lower than 0.3 is a problem. And you can see here that compassion's okay. Assertiveness has a tolerance value lower than 0.3. Dominance does, and self-reliance does. So we've got 3 variables there that have problems with multicollinearity. So we need to consider removing one of them. Now, in this analysis, we're predicting self-worth. And so you can either remove a variable because you think it statistically is the most disruptive, or you can remove a variable for conceptual reasons. You think it has less relationship with the DV than the other variables. So in this particular instance, we're going to remove the variable dominance because we think dominance has less relationship with sense of self-worth than the other variables. Dominance is your attempt to control others and influence others, and that hasn't got much to do with sense of self-worth. It hasn't got as much to do with sense of self-worth as your compassion and warmth towards others, your degree of assertiveness, which is very closely related to confidence or self-worth, and self-reliance, how reliable you think you are. Those three things are clearly related to sense of self-worth, where dominance, your attempt to influence or control others, is not. It's a different concept. People who are low in confidence may attempt to control others, so it's not so closely related. So we're going to remove that variable and then rerun the analysis and check for any issues with multicollinearity once we remove that variable. So we go down to linear, remove dominance, press OK, and check for tolerance again. So here you can see now all the tolerance figures are okay. They're all well above 0.3. So that's going to be our regression. They're the 5 variables we're going to include: age, sex, compassion, warmth, assertiveness, and self-reliance. So make sure here you put a note here. Dominance was not included. The reason why is because it showed multicollinearity with other variables and it's less conceptually related to the DV than the other variables. So now we need to think of a two-stage hypothesis, and we need to write the hypothesis. The hypothesis needs to take the form of variables A and B affect variables B and C and D, which in turn affect the DV. Or it can take the form variables B, C and D mediate the relationship between variables A and B with the DV. So a mediation of type hypothesis, and you can express it in either of those two ways. Now let me see, I might have this written down clearly so I can show you what I mean by that. So here, this is a guideline to the practical test. You can see here, variables A and B, or A, B and C, affect variables C, D and E, which in turn affects the DV. That's a perfectly acceptable form for the hypothesis. Or it can be variables C, D and E mediate the effects of A and B on the DV. So the first form is much less confusing, so I would encourage you to stick with that if you can. So I felt like an obvious distinction here was age and sex should go together because they are demographic variables, and then the remaining 3 should go together. So you might say age and sex affect compassion, warmth, assertiveness and self-reliance, which in turn affect self-worth. So that's a two-stage hypothesis. In our answer document we would say, hold on, just let me bring up the questions again. We would say type the variables age and sex here, and then the 3 mediators here, and you need to discuss why you've chosen this particular order, which is basically providing the hypothesis. So it is hypothesized that age and sex affect compassion, self-reliance and assertiveness, which in turn affects self-worth. Okay? Now we might need to discuss this in a little bit more detail, so let's just have a look at the solutions. So for this discussion it says, I'm hypothesizing that age and sex affect sense of self-worth indirectly through their impact on compassion, assertiveness and self-reliance. That is, age and sex affect compassion, assertiveness and self-reliance, which in turn affect sense of self-worth. So that's basically just stating the hypothesis in 2 different ways, and those 2 different ways are the 2 ways that I was talking about when we were looking at the approach to the practical test, that hypothesis there and that hypothesis there. Okay, so now let's run this regression. So we go analyze, regression, linear. Going to keep age and sex in the first step. In the next step we'll put the remaining predictors, compassion, warmth, assertiveness and self-reliance. Go up to statistics, make sure you've got all of that selected. I normally select case-wise diagnostics, you guys probably don't do that. Make sure you plot your predictive against your residuals to make sure to test for your assumptions. Select histogram and normal probability plot. Don't worry about that. I would normally select null-Helenius distance, but you guys haven't gone into detail on that. And don't worry about that, so press OK. And then, so there's your results. You don't actually need to run the regression for this, but you do need to produce the the question at no stage asks you about the results of the regression. So we've already answered question 2. Question 3 then says, produce the appropriate graphs to test the linearity equality, the linearity equivariances and normality assumptions. Do these assumptions appear to be met? So we've run the regression and we've produced our normal probability plot and our scatter plot. Now, in the results, the scatter plot actually has an outlier over here which we don't have, and even if I run the regression saying, which you guys I'm pretty sure have not been taught to do, but even if I run the regression saying exclude cases pairwise, I still don't get the outlier that turns up in these solutions. But I will contact the Swinburne Academic about it. Now, I thought that this graph was perfectly acceptable. I'd probably use it, but for the purposes of this unit, we'll say it's not acceptable because it's not perfect. So you can see there's a diagonal sort of shape to the layout of this data, whereas if there was equality of variances, you'd have a nice line, a little collection of data points, a horizontal line, and there was a collection of data points around the middle, and then there'd be an equal spread for each predicted value. There'd be an equal spread of residual data points across each predicted value, which you can see that there isn't in this case. It's actually this sort of square shape that's on an angle, which suggests that the distribution of residuals is larger for lower values of the predicted value, and the distribution of the residuals, or the actual, sorry, not the distribution, but the value of the residuals is larger for lower predicted values, and the values of the residuals is higher for the values of the residuals is lower for higher predicted values. There's a negative relationship between the predicted and residuals, which means that equality of variances is violated, and this means that you can't use the normal probability plot to test the assumption of normality. You can only do that if there's equality of variances, because you really need to check normality for each value of the dependent variable. But because that's a difficult process, instead we just look at the normal probability plot for the expected and for the predicted and residual values, which you can only do if there was equality of variances in the first place. So just as a little comparison, I'll show you in the textbook what a residual versus predicted scatter plot looks like when the assumption has been met. So you can see what I mean by the distribution of the points. It's taking a little while to load. Okay. Maybe that wasn't the best way to do this. So here's a scatter plot where the data, there is equality of variances. So you can see there's a collection of dots around the middle, a horizontal line where the dots are quite thick, and then they spread out to up and down along the residual axis quite evenly for each of the predicted values. So it takes on a sort of square shape instead of we've got a rectangular shape in our output, but it's on an angle. So you can see it differs a little bit. So you just need to make note of that. So if we were to look at the solutions and see how the question was answered, it says the scatter plot of residual versus predicted value shows a violation of equal variances but no violation of linearity. So the normal probability plot of residuals can't be used to test normality because the equal variance assumption is not met. So you can see that the distribution of data points is not quite equal for each of the predicted value points. But we didn't end up with this outlier here, so I'm not sure why. I'll have to ask about that. So yeah, that's it.